Cool, thanks. Yeah, it's a little early on Sunday. Yeah, we're going to be rolling old school today with some ARP. So I know hacking ARP has been around for a bit. We're going to kind of go over some of the classic attacks and then a little bit of a twist on some of them, a little bit more effective here and there. Some of the tools that are out there that do things like ARP cache poisoning and stuff like that don't really take advantage of some of these techniques. So going to go over that. So first we're going to start with kind of a background on ARP. For most of you, this is probably going to be pretty basic, but it's kind of essential to build what really ARP is and what it does and how we can attack it. So obviously network systems, like in a network, need a way to talk to each other. And a lot of times we think of them talking to each other via protocol address, like IP addresses. But on a local area network or a physical network, they actually have to talk via physical addresses. And so we need a way to translate from our protocol address, like our IP address, to the physical addresses, like MAC addresses. ARP in this particular talk, in reference in this talk, we're talking about ARP over Ethernet and in reference to IPv4. So ARP can work in other environments, but we're specifically talking about that particular environment right now. So the address resolution protocol allows us to resolve a hardware address from given a protocol address. So if we have an IP address like 192.168.1.100 and we want to talk to it, we can send an ARP request packet out to the broadcast of the network. It's kind of like a who has 192.168.1.100. And every host on the network, since it's sent out to the broadcast, gets this particular request packet. And if their protocol address matches the protocol address in the field for the target protocol address in the ARP request packet, they send out a response to the sender saying, I'm at blah, blah, blah. So here, 192.168.1.100 sends out that they're at the hardware address 00DF1A9CA378. So, okay, so now we have a way of translating between protocol addresses or IP addresses and hardware addresses. But obviously, there'd be a lot of chatter on a network, unnecessary chatter on a network, if for every packet or every frame that has to go out on a physical network, we have to send out an ARP request and receive an ARP reply. So hosts, in order to overcome this overhead, have local caches of MAC address and IP pairs. So it's the ARP cache. What this does is it just, once we've resolved an IP and MAC pair, we cache it for a certain period of time locally so that when we go to communicate to another host again, we look in our table, and if the ARP entry exists, then we know where to go. We don't have to send out an ARP request again. So this is where really part of the weaknesses in ARP kind of starts out is that particular table. So we'll go over a little bit of a background and anatomy of an ARP packet to begin with. So this is kind of a typical ARP packet. One of the first field is hardware type field, and so this specifies what the underlying type of hardware that we're sending our frames on is. Typically, in our environment, that we're talking about today, this is going to be set to the code for Ethernet. Next, we have the protocol type, which again specifies what protocol we're using. So this will be filled with the code for IPv4. Then the next two fields are hardware length and protocol length. So because we can use different protocols and different hardware mediums in order to send ARPs over, obviously the associated addresses can vary the length of those addresses. So we need a place to specify how long each field should be as far as the protocol length and the hardware length. So that's done in these two fields. We'll go over actual examples of ARP packets in a little bit, and what values go in there. The next is going to be the opcode, and this is typically going to be either a request or a reply. So this is where in the packet we specify what kind of packet we're sending. If we're sending an ARP request or if we're sending an ARP reply, and that's how the associated hosts translate that packet when they receive it. The sender hardware address is pretty self-explanatory. This is the hardware address, or MAC address in our case, of the sender's Ethernet card or interface card. So whoever's sending out an ARP request or an ARP reply, they put their own hardware address of the interface it's going out into this field. Same thing with the sender protocol address. This is, of course, how in your typical or standard ARP conversation, not we're going to abuse these fields a little bit in order to get what we want out of it. So then you have the target hardware address, which is pretty self-explanatory again. It's the hardware address or MAC address of the target we're sending our packet to, and target protocol address, which would be the IP address of that target. So as an example, if 192.168.1.20 wants to speak with 192.168.1.100, they send 1.20 will send an ARP request packet out to the local network broadcast, and this is what the packet will look like. We see that the first field, the hardware type, is set to 01, which is the code for Ethernet. The protocol type is set to IP. The Ethernet length is set to 6 because it's 6 bytes for an Ethernet address, and the protocol length is 4 because it's an IPv4 or 4-byte address. We also see the opcode is 1, which is the code for an ARP request, and then we have all the different the sender hardware address, which is the requester's hardware address, and their IP address in the protocol, the sender's protocol address, and then target hardware address, which here is set to null because that's what we're trying to do. We're trying to resolve the hardware address for the IP address that we have, so that's set to null and sent out on the wire. And then we have the IP address that we're trying to resolve in the target protocol address. So the response looks like this. 192.168.1.100 replies, sends out an ARP reply with its hardware address, 00AABBCCDDFF, and it's specifically sent to 1.20 and to its the target. You can see that the target hardware address and target protocol address are both filled out correctly, and the sender hardware address and sender protocol address are filled out with the host that's answering. This then, in turn, the host 192.168.1.20 will take that and enter it into its ARP or update its ARP cache for 1.100. So now it knows who belongs to 1.100 and doesn't have to send out more requests until a timeout occurs. So traditional ARP attacks. One of the most common ARP attacks for taking over really any local area network is ARP cache poisoning. ARP cache poisoning is, since ARP is completely unauthenticated, you might have noticed as we were talking about, even if you're not familiar with ARP cache poisoning, the dangers as we were talking about, a host sends out an ARP request and it receives, somebody else sends out an ARP reply, and when it receives that ARP reply, it updates its cache. It has no sort of authentication to verify who actually sent the ARP reply, so it doesn't really know who it's talking about to. And that's what ARP cache poisoning is really about. You basically, since it's completely unauthenticated, whoever sends a reply to the requester first wins and gets their information, or whether it's legitimate or spoofed, input into the ARP cache. We have another condition, though, where sometimes the ARP cache can be updated with gratuitous ARP replies. So even if the host didn't send out an ARP request and it's just humming along, and receives an ARP reply, then it'll still update its cache because it's dumb. So so basically, that's really what most of the ARP cache poisoning tools rely on. Instead of waiting for an ARP request to go out and trying to race with the actual owner, it just sends out gratuitous ARP replies in order to try to update the cache. This isn't effective on all operating systems, but many operating systems, this is the case. So basically, you just, in order to exploit this, you just send out forged ARP reply packet to a victim. You put in the legitimate or sender protocol address, whatever you want to hijack the connection of, and your MAC address or some other MAC address, and effectively poison the ARP cache so that the victim is now talking to you when it thinks it's talking to Joe Blow Gateway. So the results of this, as you can see, are probably the most common is man in the middle. If we poison an ARP cache entry with our own MAC address information or our own hardware information for, say, the gateway, then all the hosts or all the traffic between the host and the gateway, or any, of course, obviously any traffic going to hosts on the other side of the gateway, are going to go through us first. So we can look at it, we can modify it, we can sniff it, whatever we want to do, classic man-in-the-middle attack, and then pass it on to the gateway as if it were legitimate traffic. Sorry. Another condition with this would be denial of service. So if we put in, instead of putting in our own MAC address or a legitimate MAC address in order to hijack the connection, we can just put in a bogus or non-existent random MAC address, and now that host can't communicate with the other host. So you can sever connections between hosts. Obviously, the benefits of that can either be just simply for fun or malicious, or if it's used in conjunction with other attacks. Like, say we're attacking or attempting to exploit a vulnerable server, but we know that we're already on the local network and we know that the server is logging to some central syslog server or reporting to some central intrusion detection sensor, then we can sever that connection, deny service between those two hosts, and now prevent that external logging as we carry out the rest of our attack. So an example of man-in-the-middle attack would be client sends an ARP request for 1.1, and we can see that it's a standard ARP request packet. So we have the sender hardware address and protocol address, which are our victim host, and then target hardware address, again, is null, and we're looking up 192.168.1.1, and it's a request packet, as you can see in the opcode field. Now, before 1.1 responds, the attacker now sends an ARP packet directly to 1.20 at 00AABBCCDDEE and says, hey, I'm 1.1. And it gives it its MAC address, so 00AABBCC01AA. So now, the attacker is actually, the victim, 1.20, is talking to the attacker, where it thinks it's talking to the gateway or 1.1. So the attacker can do anything it wants with that data stream, inject things in, sniff on it, gather usernames and passwords, anything that's relevant. Again, an example of denial of service would be that 192.168.1.20 requests the hardware address of the gateway. Again, same packet. And the attacker, instead of replying with his credentials in order to perform a man-in-the-middle, replies with a bogus MAC address of 00deadbeef01. So now the victim goes to try to talk to the gateway and can't. The communications channel is severed because it doesn't really know the hardware address, even though it thinks it knows the hardware address of 1.1. So it sends packets out and it never receives, or 1.1 never receives them. Another ARP attack, classic ARP attack, is a cam table overflow. And this has been around for a long time. The reason for this specific attack is that back in the day when anybody used hubs, a hub is just a dumb piece of network equipment. So two hosts communicating over a hub, all of their traffic is forwarded to all of the ports on that hub. So if you're plugged in anywhere on that hub or that physical network, you can intercept or sniff, eavesdrop on any of that traffic and that conversation. And even potentially inject things into the stream as well and things like that. So switches, though, are different. As we probably all know, that switches maintain a table. This is actually called a CAM table, or content addressable memory table. And what this table holds is a matrix of pairs between port numbers and MAC addresses that are discovered on those port numbers, along with some other information. But what's relevant to our discussion right now is that MAC address and port number pair. So the CAM table says that switch port 23 has these MAC addresses associated with it. So when an Ethernet frame arrives at the switch, instead of broadcasting that frame out to all ports, it instead looks it up in the CAM table and only forwards it to the port where that MAC address actually exists. So that kind of severs our ability to eavesdrop on conversations, because now we're not getting that traffic. Even if we're in promiscuous mode or whatever, that traffic just never ends up on our network port. So a CAM table overflow, what it does is, no matter how big your switch is, no matter what kind of enterprise switch you have, it's going to have a size limit to the CAM table. I mean, it's not going to be infinitely sized. So there's going to be some point at which it can't, it has to overflow or purge other information out of the table if it receives too much information. So basically, what you do to perform a CAM table overflow is you send hundreds or thousands of spoofed Ethernet frames with spoofed MAC addresses to the network and overflow the internal CAM table of the network switch. So here the network switch gets filled up, starts purging out legitimate data, and now when legitimate traffic or legitimate frames enter the switch, it doesn't have a pairing in that CAM table for a legitimate MAC address. So it then ends up broadcasting it to all of the ports on the switch. So effectively turning the switch into a hub, just like we were able to do before. So now we can sniff again on traffic on the local network, just like we were able to with a hub. There are weaknesses, though, with these different ARP attacks. ARP cache poisoning in particular, most all of the current methods of ARP cache poisoning in the tools that perform this particular attack, as well as different papers that identify how to do ARP cache poisoning, utilize ARP reply packets as a way to inject the falsified information into a host's ARP cache table. But as we said before, not all OSs, most will update when it just receives a gratuitous ARP reply packet, even though it didn't send out a request. But not all OSs will. Some tools have overcome this by sniffing the network, and so when it sees the first ARP request, it races to respond faster than the legitimate host in order to inject its entry into the ARP cache. A CAM table overflow obviously also has weaknesses and drawbacks. CAM table overflow requires hundreds or sometimes many thousands of spoofed frames, spoofed MAC addresses, in order to actually overflow depending on the switch that you're actually using. So obviously, if you're a savvy network engineer and you've got Ethereal running, then you can probably detect that an ARP cache or a CAM table overflow or something funky is happening on your network. It's very identifiable, very noisy, lots and lots of crap packets on your network. And we also can prevent the traditional CAM table overflow with technologies like port security, Cisco's port security, and other related types of technologies that actually can just limit the amount of the number of MAC addresses that are allowed to be identified on a given port. So if we plug into port 34 and we send out thousands of bogus frames, then port security says, oh, well, there's only 10 allowed on this particular port, and so then can either turn off the port or ignore traffic after that or whatever. So we're not able to effectively overflow the CAM table because we can't get that many frames passed. So this really kind of mitigates. This is kind of the default answer for mitigating the risk of a CAM table overflow. Again, really, the whole idea of a switch is not a security device. So, relying on that you have a switched network to prevent people from sniffing on your network is kind of retarded. But people do, and people that they rely on using port security, or they had to add port security because this was kind of an issue, along with other issues in switched networks. So we're going to go over some new, kind of not completely new, but attacks on ARP and kind of take a different approach than the traditional attacks. To do this, I wrote a tool called Arpcraft, which basically just allows us to put together ARP packets and send them on the wire with whatever information we want put into the different fields of the ARP packet. So this is kind of the different options that are available with Arpcraft. We have we can specify the interface. We specify the source hardware address, the source protocol address, the target hardware address, and protocol address. What the opcode is, whether it's a request or a reply packet. We can also specify the Ethernet source and Ethernet destination. So if we want, by default, the Ethernet source and destination match what the target hardware address and protocol address, target hardware address and source hardware address fields are. But if we, for some reason, want to put a different MAC address in the Ethernet frame than we have in our ARP packet, then we can do that with those flags. Again, we can also set the interval, so in seconds, how often we want to send this packet out onto the wire. By default, I think it's at 5 seconds. So every 5 seconds, whatever ARP packet we've built, we send that out onto the wire every 5 seconds. And then a count. We can set how many we want to send out. So if we just want to send out 1, or if we want to send out 5,000, we can set that without having to rerun the tool. Huh. This is a pretty slide. Not quite sure what the point with that was. Anyway, here's an example of using Arpcraft to send out an ARP request to the destination protocol address of 192.168.1.100, which has a hardware address of 00 AABBCCDDFF. And we want it to say that it's from 192.168.1.20 at the hardware address of 00 AABBCCDDEE. So we use Arpcraft, and we specify the interface with the -I. -SHA, we just put in our source hardware address in there, the MAC address that we want the packet to say it came from, and the SPA, the source protocol address, the IP address we want it to say it came from, and then the target hardware address and target protocol address, respectively, and then the -O flag, we want to send out a request packet. So here you'll see the tool kind of prints out a snapshot of what our packet looks like, kind of a layout of what the different fields in the ARP packet are going to look like, so that if something looks wrong, you can cancel it and maybe you made a mistake in the options or whatever. And then it just goes ahead and injects the ARP request to the wire. Same thing with this, just another example of, let's see. Anyway, okay. So another approach to ARP cache poisoning, instead of using ARP reply packets, we went over the weaknesses already to a certain extent of ARP cache poisoning, or the traditional methods of ARP cache poisoning. So again, some OSs don't update their ARP cache just when they receive a gratuitous ARP reply. Most OSs, if not all OSs, according to RFC, won't just add an ARP entry into the cache if it doesn't already exist in the cache when it receives a reply. So that's a little convoluted as far as that sentence, but basically what that means is if I'm a host and I receive a gratuitous ARP reply, because I didn't send out an ARP request, I just receive an ARP reply saying 192.168.1.1, the gateway is at, blah. Even if 1.1 is in my cache and I'm a retarded host, then I will update my cache and say, okay, 1.1 is at blah MAC address. But I'm not going to add it to my cache if it doesn't already exist there. I'll update it if it's already there, but I'm not going to add a new host to my cache just because I receive an ARP reply that I never sent out a request for. Then another weakness is along the same lines, some OSs, specifically Solaris. Solaris has kind of traditionally been kind of harder to perform ARP cache poisoning on, because the problem is that Solaris doesn't rely, they don't really conform to the RFC specification as far as what to do when you receive an ARP request or reply. If it has an entry in its table, in its local cache, and it receives either a reply or a request or whatever, it doesn't update it. If it differs from what it already has in its table, it does nothing. But instead, it just goes on a timeout. So it waits for that entry to time out, then it sends out a new ARP request and resolves it in that way. So in order to poison, you're basically stuck in this race condition as far as you have to wait for Solaris to time out its entry, then send out the first request packet and respond with a reply faster than the legitimate host in order to poison a Solaris machine. In a way, that has, if you can do it correctly, it has a certain benefit, because then that host, that entry, your forged entry, is not going to be updated by even the legitimate server or legitimate machine. It's stuck in there until it times out. We notice, though, that RFC 826, which specifies the ARP specification, says that if, instead of an ARP reply, if a host receives an ARP request, so if I am sitting along as Joe Blow host and I receive a request for my information, so my MAC address and according to my IP, and the target protocol address, of course, if it because it's sent out to broadcast, if it matches the information that I have, if it's my protocol address that it's looking for to resolve the MAC address, then before responding, first the host updates or adds the source protocol address and hardware address pair to the local cache. So again, if somebody asks me for my information, whether if I have that information, if I have their information in my cache, or even if I don't, first of all, what I do is I check if it's in my cache. If it is, then I'll update it. If it's not, I actually add their information. So basically, it's for performance reasons. So that if you don't have to both exchange and send out ARP requests, only one request initiation will update the cache on both sides. So if you send out a request to a victim or to a host, they'll update their cache with your information as well, so that they have the cache now in order to speak with you further. The actual verbiage from RFC 826, you can see there. It's pretty straightforward. It basically just says what I just said. So instead of using an ARP reply packet, we can use an ARP request packet to inject our information, the information we want, into an ARP cache in order to poison the ARP cache. So all we need is a single packet. We don't have to wait for an ARP request to come out from them and try to race with a response. All we need to do is send out a request with our information, and most hosts will just update if that host already exists in the cache. Otherwise, you can actually add new entries, where with a reply packet, it's not going to add a new entry into the cache, but we can actually inject new entries into the cache using a request packet. So here the attacker, without being initiated by the victim, 1.20, the attacker just sends a request packet to 1.20 saying it's from 1.1, but it's with the attacker's MAC address. So we see that the opcode on this packet is 1.1, or is 1, or a request. So we're sending a request packet to 1.20, and saying the sender hardware address is 00AA BBCC01AA, which is the attacker's hardware address, and then saying our protocol address is the gateway's, and then sending it to the victim, their target hardware address and protocol address. Sorry? Yes. Sorry. Huh? Oh, I'm sorry. He said, is it unicast? Yeah, sorry. I'm bad at that. So, like, throw things at me if I don't repeat the question. So, I'm going to kind of demo that. Oop. So I'm going to say, here we have our victim here is a FreeBSD box. And I'm going to just enter a random MAC address and IP pair into its cache. So here we have the current ARP cache, which has an entry for 1.1 and 1.157. Okay, so we're just injecting to 192.168.1.163 an ARP request packet from 1.2 saying that 1.2 is at 00 deadbeef01. So now we'll go over to the victim and look at the ARP cache, and we have an entry for 1.2 at deadbeef01 or 00 deadbeef01. So we can just arbitrarily enter entries into the ARP cache using request as opposed to just gratuitous reply packets. I'll demo a little further that we can overwrite 1.1, our gateway, with 00 deadbeef01 by using request packet 2. So here 1.1, now we've overwritten the gateway address with deadbeef01. So it's fairly straightforward ARP cache poisoning technique, but it's just using a different packet type, so it's a little bit more reliable on different hosts. So again, we talked about the weaknesses of some of the ARP poisoning techniques. CAM table overflows obviously have certain weaknesses. They can be prevented with port security. They can be very easily identified by an intrusion detection system or an administrator running TCP dump. It takes thousands of packets usually in order to perform a successful CAM table overflow. Do you have a question? Static CAM table entries? Static entries are usually a fairly acceptable defense for any of the, even for ARP cache poisoning as well. Static ARP entries are probably the best way to go as far as defense. It's just in your average enterprise network, you can't really create static entries for all of your hosts, so that's obviously a mitigating problem. Okay, so we went over those problems, but usually we don't really need, in a real targeted attack, we don't really need to sniff the entire network for something. I mean, it might be nice sometimes, but usually we're going after one machine or a more targeted approach, especially if stealth is in order at all. So there's a couple of ways that we could already do that. We can already inject into or poison the ARP cache of a specific host. So a man-in-the-middle attack essentially allows us to sniff as well because traffic is going through us. So it's kind of a targeted sniffing approach. That's how most people get by sniffing on a switch network without using a CAM table overflow. You just poison the ARP cache with and perform a man-in-the-middle attack, and then you can sniff on that traffic. But obviously, that's not always appropriate because now your MAC address is in the CAM or the ARP cache table of the victim, so you can forensically and further. It's just easier to identify who's actually perpetrating an attack. But a little bit back before, as far as the whole CAM table scenario, if a switch receives a frame and checks its CAM and doesn't have that pair or an entry that matches that frame, it floods it to the entire network. So we can accomplish the same thing. As opposed to flooding and overflowing the entire CAM table, we can accomplish this type of attack by just here. Again, utilizing the ARP cache poisoning technique. Instead of poisoning and performing a man-in-the-middle attack, we just poison the target with a null MAC address. And so basically, when the target sends it out onto the network, the switch doesn't have an entry in its CAM table, so it floods it to all ports again. But it still gets through. The gateway, the traffic is not going to be interrupted. So even if you're in a man-in-the-middle attack, you actually have to route the traffic back to the legitimate host. Here, it gets to all the ports, and the legitimate host is still going to pick it up because it's got a null destination on the frame. So we can kind of we can perform targeted sniffing or eavesdropping on a switched network by using this technique, and this works on every switch that is out there because it's really the underlying principle is that it looks in the CAM table, and since that pair, the null MAC address pair, doesn't exist in the CAM table, then it floods it to all the ports. This doesn't require hundreds or thousands of packets. It requires a single packet in order to inject or poison the ARP table of our victim host. So port security is not going to stop it. We're not actually even if we're sending it to multiple hosts, we're not spraying thousands of random MAC address or frames with random MAC addresses out to the network in order to overflow a CAM table. It's only a single MAC address, and so we're not using multiple entries in the allowable entries from port security, etc. And obviously, it's less identifiable. A single packet's a lot less identifiable on your network than thousands of bogus packets. Few other fun little things with ARP. some OSs can actually be poisoned with their own MAC address for the destination. So so here we can actually poison the, say we want to sever a connection or denial of service connection between a host and a logging server. All we have to do is send a request packet again with the sender hardware address, which equals the host that we're poisoning, and the target hardware address equaling the host that we're poisoning, and then the target protocol address and target sender protocol address with the hosts that we're the target would be the host we're poisoning, and the sender would be the host that we're masquerading as. And now we can basically the host doesn't even send it out to the network because it thinks it's local, and so the traffic never ends up on the switch. So it can't communicate with the log server, etc. Yeah?
You said some OSs.
Yeah.
What OSs let you do that? Don't.
Windows will let you do it. Solaris will let you do it. I don't think, if I remember correctly, FreeBSD I think doesn't do that. It actually does check if it's if it's already one of the local interfaces. So just test. I mean the tool Arpcraft is going to be released so play around with. There's other network testing tools too, like Scapy and things like that can do similar things. So here, obviously, tries to log to a a network syslog server the attacks that you've done after poisoning cache. Can't talk to the syslog server, so nobody's going to see anything other than on the local host. So you pop whatever vulnerable service and drop the logs there. Another thing that's kind of cool or kind of fun, silly. Is that if a host receives an ARP request or reply with the same protocol address as its own or one of its own on interfaces, but a different MAC address, so some other host on the network is saying that it has that IP address, then most OSs, Windows, a bunch of the Nixes, things like that, will complain to the user that whether it's via syslog or console log or in case of Windows, it actually pops up a dialog that there's a duplicate IP address on the network. So you can play games with Windows users by sending them or popping up this nice dialog or a bunch of times. Helps out social engineering attempts actually, because if you do this a bunch of times in a row or just do it in a loop, and it actually burns up quite a bit of clock cycles. I've had Windows machines just crash if you just kind of keep sending them the thing. If you just do it, for a little amount of time, and you call up as tech support and say that apparently they've been having, a conflict of IP addresses and ask for their username and password. Most people actually do it, so kind of fun. Other fun with ARP. The Kaminsky factor, got to throw in a covert channel, of course, over any protocol like DNS or ARP or whatever. So just like any protocol that has optional fields or fields that you can play with, you can throw other data in it and get it across. So we can use ARP to transmit secret information over a local area network. Basically, I had a demo, but it's the other hardware's not working. So but I do have a better demo actually. So we're actually in this case just using sender hardware address field, which is just 4 byte or 6 bytes of bandwidth per packet. I think I said 4. Yeah. I had to rewrite this stupid slide deck last night because I only brought the PDF version stupidly. So excuse any typos, please, because I wasn't not partying either. So anyway, we get 6 bytes of bandwidth per packet. Somebody's saying something, but. And then basically, in order to just kind of simply obfuscate the message over the wire, we just threw in a little bit of XOR encryption with a shared key between the client and server, and can receive secret messages. We could increase the bandwidth per packet by using more than one field, or even more simply, since like we went over, we can specify the length of the address fields. We can specify whatever length we want for the hardware address field or the protocol address field, and just stuff as much data as we want. So we could specify a length of 1024 and stuff a kilobyte of data into the hardware address field or the protocol address field, and put one packet on the network and get all the data we want. Another kind of extra thing, instead of just passing messages over the network, I kind of went a step further and threw together ARP-SH. I'm going to show you just a fun little proof of concept, remote so-called encrypted shell over ARP. So fun for backdoors. Kind of just proof of concept. It's totally buggy right now, but basically it consists of two parts: ARP-SHD and ARP-SH. And again, we just obfuscate the data so dumb network administrators can't just see our complete traffic via XOR encryption and a simple shared key. So I'll demo that. Here's our victim. So somehow we've popped this machine with whatever vulnerability or whatever. So we're going to start ARP-SHD. And over here, we'll just start a network sniffer so we can see what traffic's actually being passed. It's not actually wrapping it through telnet or some crap like that. So put that up here, and so we yay. So there's no ports listening on the victim server or anything like that. It's just monitoring ARP traffic and detecting our command, executing it, and sending it back all over ARP. You can see all the traffic here. So, fun stuff. There you go. So really, the moral as far as that goes is just you can't really trust any protocol to be what it really says it is. What we're doing there is, again, just sending the data via the sender hardware address, sending a little bit. What? 2 minutes? Oh, sorry. Well, I think we're... So ARP Venom is a tool that it kind of automates these attacks. Check didrev.org for release and updates on that. It should be up pretty soon. I don't think it's I got it posted yet. So again, traditional ARP attacks work well and they're good standbys. They have certain weaknesses. So there's certain cases where you can use some of the techniques that I showed today that would be a little bit more effective. And targeted sniffing can be, again, accomplished by poisoning with null MAC addresses for the intended destination. A lot less noisy than cam table overflow, can still do kind of the same thing. So a lot more reliable, too, for switches that have port security and things built in. So any questions? I'm sorry, can you? Yeah, the question was, if you poison a victim with a null MAC address in order to do sniffing, does the destination host, while you get the data and are able to sniff the data, is the transmission interrupted? Does the destination actually still get and process the data? And yes, in most every case, it does actually accept and process that packet. So, anyone else? Time to? Oh. Well, thank you. Thanks for your time.